So today we're covering section 4.5 in the textbook, and we are going to review exponential and logarithmic functions. So 4.5, exponential and logarithmic. I'm just going to put log functions, f of x. All right, so we're going to look at some rules that relate to this. So I'm going to start with exponential growth, like bacterial growth, for example. And what we like once we get sick is the decay model, which is when you get better. And so when we look at exponential growth and decay models, they basically have this this design. So a sub 0, remember that's always initial. And then we have e raised to the k times t, where t is time. And so there's two things, or two types. We also refer to it as future value, which is usually denoted with a, equal to a sub 0 e to the kt. The only difference here is the first part of the notation, if you notice. So if I'm looking at where k, the value k, is greater than 0, then we have a growth or increase of whatever it is, whether bacteria or finances, what have you. And if we have k, basically k is less than 0, then we have decay. We have a declining value or growth model in that case. So exponential growth and decay functions, we use these a lot in the medical field. We also use them sometimes in finance, relevant to investments. So keep these two in mind, and I mean this should be easy to remember that this is decay, this is less than, less than referring to decay. Okay, what do the diagrams look like? So if I'm looking at exponential, I'm just going to put exp, exponential growth, which is the first design that I showed you. Our value will start in the first quadrant at typically a sub 0, which is the initial value, and it's going to be an increasing function in this direction. If it is an exponential decay, then in the same notion, we have our first quadrant going like this, and our a sub 0 would be somewhere here. Remember, this is a sub 0, as is this. And basically this is decreasing in this direction. So it's going, the arrow is pointing that way. And so this would be an example of a k less than 0. This is an example of k greater than 0. All right. And so I have an example for you here, which I'm going to read the first part because it is a word problem. And they have given us the US population 1970 to 2010. And it says the graph in figure 4.22, which is exactly that. It is the diagram from the chart. It says the graph shows the US population in millions for 5 selected years. So they're looking at 1970 as an example. So they have basically in the first quadrant, they have starting with 1970, then 1980, then 1990, then 2000, and then 2010. And they're looking at the population over here. So our population is going from by 50s. So this would be 50, and then you have 100. This would be 150, and then this would be 200. You have 250, and then 300, and then the last 350. This is population in millions. So when I say 50, I mean 50 million. Okay, keep that in mind. And so then they're giving us a little bar graph, which I'm going to draw here. And let's use blue. Switch this pen out. All right, so they start with a blue 1970s, which is at about 200. So in 1970, we're approximately here, right? And so they basically have a solid bar graph. This is in the book, by the way. They're using purple for 1980, and they're putting 1980 at approximately 226, so it's about the halfway point here. So let me just try to match it as best I can. I'll give you the exact numbers in one moment. And so this is just to give you an idea of what they're giving you. 1990, we're almost at 250,000, so it's slightly higher than the 1980, but just a smidge below 250, and I'll give you that number in a minute, exact number. Then they give us, let me change this to orange. Okay, in orange we have the year 2000, heading close to 281, so very close to 300, so let's put it about here. I'm doing the best I can to match the graph. And then in kind of a funky yellow, let's go with this one. We're at 308, just over the threshold of 308,000. So let's see. I'm doing the best I can to draw the graph just like it looks. All right, so let me give you the numbers again. So for the first year, they're giving us 203.3, and for this year, 226.5. For 1990, we're at 248.7, and 2000, we're at 281.4, and lastly at 308.7. Okay, so those are the numbers they gave us. And so here's what they're telling us. The U.S. population was 203.3 in 1970. By 2010, it had grown to 308.7. It says, find an exponential growth function that models this. So for part A, they want you to model this. Model the change basically from 1970 to 2010. So again, part A, find an exponential growth function that models the data for 1970 to 2010. So we know that we're going to have the future value, which is going to give us 203.3, which is our initial value. So this is the a sub 0 part of the formula. Natural base E, that is just what it is. It is what it is. We know that the difference between 1970 and 2010, so if we take 2010, take away 1970, that the difference in time is 40. So we know that that's T. And then in this case, we also need to find, so this will be 40K. And we then substitute in the values knowing that we're going to end up at 308.7 because technically this value is already known. It is 308.7, which will help us find K, which is what we want to find. And so in doing that, we will use 308.7 is equal to 203.3 E to the 40K, because these are things we do know. We now need to find K. And step 1 would be obviously to divide by 203.3 on both sides. Okay, and so at this stage we have e to the 40k is equal to all of this, which is basically 308.7 divided by 203.3. Now, remember when I stated that you could simply just put natural log on both sides? And in doing so, what you end up with is 40k on this side is equal to the natural log of 308.7 divided by 203.3. And so the only thing we'd have to do to find k now is to divide by 40. So k is equal to the natural log of 308.7 divided by 203.3, and all of that divided by 40. Now if you use your calculators, take a moment, do natural log of 308.7 in parentheses divided by 203.3, and then hit enter and then divide that by 40, and you will get approximately 0.01 for k. And therefore your final answer is going to be that future value is equal to 203.3 e to the 0.01 times t, which is 40 in this case. Okay, since they want the model, we don't put 40 because now we can use that model for future years. So instead of 40, we'll put t because that'll give us future values as we adjust. Now, and then they're asking in part B, if you don't have further questions on this, in part B, they're asking, by which year will the U.S. population reach 335 million? So when will we reach 335 million? So they're basically asking, what is time? By what year based on this model? And since we have the model, we're going to say 335 million is equal to 203.3 e to the 0.01, and then this is their question, what time? So we begin with a similar process. We're going to divide all of this by 203.3 on both sides. Okay, and that'll cancel, obviously, leaving you basically e to the 0.01 t is equal to 335 divided by 203.3. So once again, we take the natural log of both sides. We'll take the natural log here and here. This will cancel. And we're going to be left with 0.01 t is equal to the natural log of 335 divided by 203.3. And second to last step is we're going to find t by dividing by 0.01 on both sides. So 0.01. This leaves us t is equal to the natural log of 335 million divided by 203.3, and all of that divided by 0.01. You should get approximately 50 years. Okay, and so that is the gist of this question. It takes a little bit of time when you do it at first. All right. The other question they propose to you is the carbon question with the Dead Scrolls. And so very likely this will be a decay question. So let's take a look at this one. This is example 2. Carbon dating, basically. And so in this one, in part A, it says, use the fact that after 5,715 years, a given amount of carbon-14, I'm just going to put C14, will have decayed, so it decays, like I said, to half of the original value for carbon decaying. Okay, so in this case, we want to set up the model. So if we set up the model, we know the original model is future value is equal to that initial value times e raised to the k times t. Since in this case we're going to decay by half, this becomes half a over 2, indicating this part of the question. And that is equal to a sub 0 e to the k times 5,715. Okay? And so, given the fact that we have a on both sides, we can actually just divide both sides by a sub 0, and we end up with 1/2 is equal to e raised to the 5,715k. We're obviously solving for k. So if we take natural log on both sides, and this is a process you'll follow in every one of these questions, you'll find that you'll have natural log of the 1/2 equal to the natural log of e to the 5,715k. And so remember, both of these tend to cancel each other out on that side. And this is going to leave you with natural log of 1/2 is equal to 5,715k. And so to solve for k, you're going to simply divide by 5,715 on both sides. So the only thing I can recommend to you on these types of questions, so that we don't drive each other crazy, is just follow the pattern and the process. This is going to give you a negative 0.000121, and this is equal to your k value. So if I were to do the model for this, now knowing k, then I would simply say this is future value is equal to that initial value times e to the negative 0.000121 times t, because now we don't know t. They follow up the question, of course, asking you, well, in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found in Arab Bedouin herdsmen. Analysis indicated that the scroll wrappings contained 76. So in part B, they're giving you a percentage. They're telling you it contains 76% of their original carbon-14. So if we want to estimate at this point what is the age of the sea scrolls, okay, so we would simply take the model, which is 0.76 times a equal to a sub 0 e to the negative 0.000121 t. Remember, this is 0 point, right? And so in this case, again, the a's cancel themselves out because they're on equal sides of the equation, just like we did here. Believe it or not, we actually cancel these out, leaving the 1 by itself in the previous example. So we now have a question that relates like this. It says 0.76 is equal to e to the negative 0.000121 and t, which we're looking for. All right, because remember, these are all legitimate values. If we take the natural log of these two values on both sides, again, remember, these two cancel each other out. That never changes. And so we're left with natural log of 0.76 equal to negative 0.000121 t. And so if I'm solving for t, I'm going to simply divide by negative 0.000121 on both sides of this equation. This will cancel out and you're left with t equals this, and therefore t equals 2268. All right. So as I continue this video, going on to number 3, yes, there's yet another formula that I have to throw your way. This formula is in example 3, and it has to do with logistic growth models and so the two formulas that you are going to need to learn really well are the two that I'm going to put right here, where you have f of t is equal to c over 1 plus a times e raised to the negative bt. In this case, c has to be greater than 0 and b has to be greater than 0, so they cannot be 0 and they cannot be negative. Or the same model, which is a is equal to c over 1 plus a times e raised to the negative bt. Okay, so I want you to understand that in this equation, as our time t in both of these models increases, so it heads towards positive infinity, the model approaches 0 and gets closer to c. So this approaches c, or you could put the model approaches c. And let me show you an example. So in example 3, you have f of t given to you as equal to 30,000 divided by 1 plus 20e raised to the negative 1.5 t. Now what this describes is the number of people f of t. So this is the number of people who have become ill with influenza in T weeks. It says after its initial outbreak in a town with 30 inhabitants, the first question is, so part A, is how many people became ill when the epidemic began. So how many became ill at the beginning? Think of it that way. Kind of like COVID. So in this case, since we know we're looking at f of 0, where time is initial, we have 30,000 over 1 plus 20e raised to the negative 1.5 times 0. Because remember, that's basically going to be 21, right? Because this will cancel out to just 20. So this gives me an equation where f of 0 is actually equivalent to 30,000 divided by 1 plus 20, ergo 21, which is approximately 1,429 individuals. This is how many people were initially ill when the epidemic began. All right, in part B, it says how many people were ill by the end of the 4th week. So in B, how many became ill after 4th week? All right, so in the same fashion, we would take our model, which in this case would be f of 4, so I guess time is in weeks. So f of 4 is equal to the 30,000 divided by 1 plus 20 raised, or times e raised to the 1.5 times 4. And so this becomes approximately, once you use your calculator, 28,583. So approximately 28,583 people were ill at the end of the 4th week, compared to the original amount of 1,429 that were ill at the beginning of the epidemic. Okay, and so part C simply asks us, what is the limiting size of f of t the population becomes ill? So I'm going to write this one down. So it says basically, what is the limiting size? I'm going to write it over here so I don't confuse the work numbers. What is the limiting size of f of t meaning the population that becomes ill? Okay, so in part C, what you'd want to consider is our equation, our original equation. So in this case is f of t is equal to c over 1 plus a times e to the negative bt. The constant c is the limiting size. In our equation, 30,000 is our limiting size. Okay, remember what they said to you here at the beginning. As t approaches infinity, then our equation approaches c, because this becomes so unbelievably tiny that this would have to become our value. All right. So that is number 4. Or example 3. Example 4. In example 4, it says choose the model data. The data which indicates the ages 1 to 11. The human brain does not grow linearly or steadily. It grows scatterplot-like. A scatterplot for the data is shown. What type of function would be a good choice for the model? And so if you look at the model, and I'm going to actually have to draw this for you because they give you a chart, and I'm just going to actually give you the numbers and you're going to create the chart. So, and then this is the percentage of brain size, which is why I believe in some cases we have education backwards, because you guys we all go through age progressions where when we notice we have spurts of brain growth, body growth. Okay, so we have 1, 2, 4, 6, 8, 10, 11, and respectively, these are the percentages of the brain growth. I'm drawing the line so that you can follow the pattern because it's not nicely columned. So I just want to make sure. All right. So that's your brain growth at that moment. Okay, and if you diagram it on an Excel, which I can do for you using Excel, if you want to do it with me together, we could. Let me open up my Excel, and I'm going to show you what the scatter plot for that data would look like. All right, so I'll go to Excel. And I'm going to try to replicate what they have here. Let's see. So again, I'm going to put age here just to help you follow along. And this is going to be the percentage of brain size. All right, so we'll go with age first. So 1, 2, 4, 6, 8, 10, 11. And then here we have 30, 50, 78, 88, 92, 95, and 99. Okay. So I'm going to grab this information and I'm going to go to Insert, Scatter Plot. Let me see. Yeah, it looks good enough. So you could say that this is a percent in brain size versus age. Okay, so understand that the y-axis is the brain size and the age is actually the x-axis. So this is the diagram they have in your textbook. So then the question they asked you was, what type of function would be good, a good choice for modeling the data? Well, if you use your line reg, you'll find that it'll actually spit out the answer for you. So in other words, unless you have a graphing tool, I don't think that'll be easy for you to use or easy for you to do without the graphing tool. If you don't have a TI-83, I do not expect them to actually give you this question. But because this concept happens to be logs and logarithms, I would expect you to at least say that this has to do something with logs and logarithms. So in this example, we can argue, now my calculator would give me to use y equals a plus b natural log x. And that would be the function you would input given this information. My calculator also spit out that a is approximately 31.954. I'm going to ignore the other 3 decimals. And that b is equal to 28.9473391. Now, I hate to say this to you, there is an actual value you can obtain. These values can be obtained with formulas, which are fairly easy. The regression formulas, for example, are very helpful. You do have a correlation coefficient of 0.99, which says that there is a direct association. You have a coefficient of determination, which is approximately 0.98. These are all statistics concepts. And while, yes, we're introducing it to you, no, I would not expect you to do that without some sort of graphing technology. So a graphing calculator would definitely come in handy. If you guys remember at the beginning of the term, I did say to you that there is an emulator called WabbitEmu. If you download that to your phone, it actually functions just like a regular TI-8384 calculator. Keyword. And it's free. Okay, so examples 5, 6 are all the same. So I'm actually not even going to bother with those. I think you're better off, doing those in your homework assignment. There is one other example that I want to do with you, which is example 7. In example 7, in this case, we're talking about expressing an exponential model in base E. So I am going to cover this briefly. Sometimes the pen does what it wants. So expressing an exponential model in base E. So they give us a function just to talk about it. And so I'm going to start with some of the basics where y is equal to abx raised to the x power, which is equivalent to y is equal to a times e raised to the natural log b times x. All right, and so they start you with that. They do give you a model here. They tell you in this example that g of x as a model is equal to 2.577 times 1.017 raised to the x. And so in this case, they want us to rewrite. So rewrite as a function with base e. And so in our case, we would simply rewrite this as g of x is equal to, notice the writing, and this reason I'm doing this in this order. So we would start with g of x, since they want it in base e, equal to 2.55 e raised to the natural log of 1.017. All right, and then raised, or times, in this case, times x. So notice that the slight changes in when we express this. This you do need to know how to do without technology. You should be able to do that. Okay. If I gave you another one to try, just for the sake of making sure that you got this. So these are called rewrite, basically, as an instruction. So I'm going to ask you to rewrite this one, where we have y is equal to 4 times 7.8 raised to the x. So we're going to rewrite this in terms of base e. Right? And so in doing so, I'm going to actually do this underneath so you can follow me. So this simply becomes y equal to 4 times e natural log of 7.8 x, or times x, however you want to do it. If I were to actually work this out, this would become y equals 4e raised to the 2.054 x. Okay? So that's the notes for 4-5 in a nutshell. 4-5 is a little bit tougher, but practice and write every question down as best you can. Make a logical connection between them.